Okay, let me try to prove the second part of the Hermit theorem. But before that, please subscribe my channel and please watch all videos in my channel online and do not try to download them. For the continuation of the proof, let me start to prove the uniqueness of the Hermit interpolating polynomial. So I want to prove the uniqueness. Okay, for the uniqueness, let h2n plus 1 of x be a Hermit polynomial. And let p of x be another polynomial of degree 2n plus 1 such that p of xi be equal to f of xi and p prime of xi be equal to f prime of xi for I equal to 0, 1 to n. Okay, so in fact I supposed that there is another polynomial of degree 2n plus 1 that satisfies in in fact Hermit interpolating polynomial. Now set e of x the difference between h2n plus 1 of x and p of x. Okay, it's clear that e at every nodal point, e of xi in fact, is h2n plus 1 at xi minus p xi, and we supposed that p of xi is equal to f of xi, and also we know that h2n plus 1 xi is equal to f of xi. So this difference is equal to 0. Okay, and also if we consider e prime of xi, e prime of xi, this is equal h prime 2n plus 1 of xi minus p prime of xi, and also by our assumption and by the property of h2n plus 1, these two items are equal to f prime of xi, and this is also equal to 0, and these two relations are correct for I equal to 0, 1 to n. Okay, so this means that e of x have n plus 1 roots of order 2, because e of xi equal to 0, e prime of xi is equal to 0, and we know that this property in fact guarantee that the order of the root is from the second order. So I can write here, so e of x has n plus 1 roots of order 2. Okay, it means e of x has 2 times n plus 1 equal to 2n plus 2 roots. And we know that because e of x is the difference between two polynomial of degree at most 2n plus 1. So the degree of e of x is at most 2n plus 1, and a polynomial of degree at most 2n plus 1 has at most 2n plus 1 0, and here because it has 2n plus 2 zeros, so e of x should be 0. Okay, so I can say here, but degree of e of x is equal to 2n plus 1, and e of x has 2n plus 2 roots. This is not possible unless e of x be equal to 0. So p of x minus h2n plus 1 of x should be equal to 0, and it means that h2n plus 1 of x should be equal to p of x, and this guarantee that the order, the uniqueness of the Hermit interpolating polynomial. This is the second part of the proof. It just remains the error term for the Hermit interpolation. So let me continue proof error. Okay, for the error term, we have to prove that f of x minus h2n plus 1 of x equal to f2n plus 2 at c over 2n plus 2 factorial times I equal to 0 to n x minus xi squared, and we know that there exists such xi in the open interval of a and b. Let me call this equation number 1. It's clear that if x be every xi point, it's clear that f of x minus h2n plus 1 of xi, the left hand side will be 0, and also the right hand side will be 0 because of the existence of term x minus xi. If you put xi instead of x, so this term will be 0, and because this is a multiplication of some parentheses, all of this term will be 0, and 0 equal to 0 happened. Okay, so let me write it. If x be equal to xi, then the equality 0 equal to 0 happened, and it's okay. So let x is not be equal to xi and define. Now, we define a function like g of t equal to f of t minus h2n plus 1 of t minus t minus x0 squared times t minus xn squared over x minus x0 squared times x minus xn squared times f of x minus h2n plus 1 of x. Okay, we define a g of t like this. It's clear that g of xi is equal to 0. G of xi equal to 0. Why this is true? Because if you put instead of t xi, so I get f of xi minus minus h2n plus 1 times xi. This will be f of xi, and also this one will be f of xi, and the subtraction of these two terms will be 0. And also if you put xi instead of t, one xi will appear in one of these parentheses and vanish all this term. So g of t, g of xi will be 0. Okay? Also, g of x is equal to 0. Put instead of tx, f of x minus h2n plus 1 of x. The numerator and denominator are same, and we cancel both, and it remains 1. So it will be f of x minus h2n plus 1 of x minus f of x plus h2n plus 1 of x, and this is also clear, and it will be 0. Okay, so here I have n plus 1, 0, and here 1. So we have n plus 2 zeros, n plus 2 zeros for g of t equal to 0. Okay, so by Rolle's theorem, we have g prime of t should be equal to 0. G prime of t equal to 0 has n plus 1 distinct zeros, xi0 to xn, in open interval of a and b. In other hand, g prime of xk is equal to 0. G prime of xk will be equal to 0 if you take derivative f prime of t minus h2n plus 1 of t and something more, and if you compute, you can see that g prime of k will be equal to 0 for all k equal to 0 to n. Okay, so g prime of t equal to 0 has 2n plus 2 roots, like c0 to xn and x0 to xn. Okay, so since g prime is 2n plus 1, let me clear it. So g prime has derivative up to 2n plus 1. So by Rolle's theorem, in fact by the extended Rolle's theorem, there exists xc in interval a and b such that g2n plus 2 at xc is equal to 0. Now let me compute the 2n plus 2th derivative of t. It will be f2n plus 2 at t minus h2n plus 1, 2n plus 2 at t minus, and here if you have a look at this polynomial, you will get in fact you can find a polynomial of degree 2n plus 2. So if you take derivative from a polynomial of degree 2n plus 2, 2n plus 2 times, it just remains 2n plus 2 factorial in the numerator, and the denominator will be keep like before. Okay, so it will be t here, and minus 2n plus 2 factorial over x minus x0 squared times x minus xn squared times f of x minus h2n plus 1 of x. Okay, so if you put g2n plus 2 at c, okay, it will be, okay, now here f2n plus 2 at c, and also we know that if you put xc here, this derivative of a 2n plus 1, a polynomial of degree 2n plus 1, vanishes to 0. Okay, so it remains minus 2n plus 2 factorial over x minus x0 squared times x minus xn squared times f of x minus h2n plus 1 of x. And also we know that here the left hand side should be 0. So if you compute f of x minus h2n plus 1 of x, it will be equal to, in fact, f2n plus 2 at c over 2n plus 2 factorial times x minus x0 squared times x minus xn squared, and this is equal to f2n plus 2 at c over 2n plus 2 factorial times pi I equal to 0 to n x minus xi squared, and this complete the proof. Okay, these complete the proof. Now let me just give you an example about the using of this theorem. Let me try to find an interpolating polynomial. Okay. Using the theorem, find Hermit. Interpolating polynomial for this table. Let me consider x0 and x1. Okay, x0 be 0, x1 be 1, and also f0 and f1 be equal to 1 and 3, and also consider f prime of 0 be minus 1 and f prime of 1, f prime 1 will be 2. Okay, I want to find the Hermit interpolating polynomial. Okay, by the theorem, the order of h2n plus 1 should be 2n plus 1. Here n is 1. Yes, here n is 1. So degree of h2n plus 1 should be 3. Okay, so in fact I am looking for a h3 of x. Okay, I have to find this one. Now let me start. h3 of x is equal to h2 times 1 plus 1 of x, and this is equal to j equal to 0 to 1 f of xj times h nj. N is 1 and j should appear here of x, plus sum j equal to 0 to 1 f prime of x j h hat 1 and j at x. Okay, so if I open these two sigmas, I will get this is equal to f of x0 h10 of x plus f of x1 h1 and 1 at x plus f prime of x0 h hat 1 and 0 at x plus f prime at x1 h hat 1 and 1 at x. Okay, sorry for the ring of my mobile phone. Let me continue. Here, we know that f of x0 is f0, and we know it. f0 is 1. So it's f0 equal to 1. F of x1 is f1, and this is equal to 3. So let me put it. F prime of x0 is f prime 0, and it's equal to -1. And finally, this one is f prime 1, and it is 2. So it just remains to compute this term, it remains to compute this term, okay, this term, and finally this term. I have to compute these terms. So let me just rewrite it to form. This is equal to h 10 of x plus 3h11 of x minus h hat 10 of x and plus 2h hat 11 of x. Let me compute every of these terms. First, let me compute h10 of x. This is equal to 1 minus 2 times x minus x0 L prime 1 0. This is by the definition of h nj. You can refer to my previous lecture and find the formula for h, and you can use it. This one times L10 squared of x, and this is equal to 1 minus 2 x times minus 1 and times minus x squared, and this will be equal to 1 plus 2x times 1 minus x squared. In the same way, I can compute all of other terms, okay? And if you do this, you can find h1 1 in fact. And note that here you have to compute some extra computation for computing L10 and L prime 10 and so on. You know it, and you can do it by yourself. And if I try to compute H11 of x, it will be to form 1 minus 2. Let me write the final form and I avoid the computation. 3 minus 2x times x squared, and also I need to compute h hat 1 of x. This is equal to x minus 1 times x squared, and finally h hat 1 0 at x, it will be x times 1 minus x squared. Okay, finally, if you put together all of these terms in this formula, you can get the interpolating polynomial to form minus 3x cubed plus 6x squared minus x plus 1, and this is the Hermit interpolating formula that we were looking for it. There is another technique to finding the Hermit interpolation. Maybe it's a little easier. Maybe in the next lecture I mention this technique. But until the next lecture, please subscribe my channel, please watch my videos online and don't try to download it, and please introduce my channel to your friends and your colleagues. Thank you very much, and wait for the next lecture.